To another video where we work through some past paper exam questions for the Edexcel Core 3 Maths A-Level syllabus. In this video we will tackle the questions which have arisen in regards to exponential growth or decay. As always, pause the video, attempt the question and then work through my solutions and correct your work. Let's start straight away. Okay, in this question we're told that if you invest £1 into a savings scheme at a rate of 4% per year, after X years you would have Y is equal to 1.04 to the power of X in investment. It asks us to sketch the graph and do various other things. So I'm going to do bit by bit. Anything, remember, of the form Y is equal to AX, where A is a positive number, looks like this and crosses at 0, 1. So we know our graph is going to look something like this where A is 1.04. However, we're told that X is bigger than or equal to 0 because it's the number of years. So if we were drawing this, we've got to be very careful. Make sure we make the graph start here and go up exponentially as such. And this would be the graph Y is 1.04 to the power of X, and this point here is X is 0 and Y is equal to 1. It does not go this side of the axes, it just goes where X is bigger than or equal to 0. You're asked to calculate the interest, calculate to the nearest pound the value of an investment of £800 after 10 years. Well, in the previous slide we're told that if you invest £1 initial investment, then after X years you would have that Y is equal to 1.04 to the power of X. And that's if you invest £1. So you can think of this as this amount here is for each pound. Now, if you're investing £800, you might have a new function, we might call it Y is equal to 800 times 1.04 to the power of X. Because for each pound, your return is 1.04 to the X, but you've got 800 of them, so Y is equal to this. Therefore, after 10 years, Y would equal to 800 multiplied by 1.04 to the power of 10. Tap that in your calculator, and you should get yourself Y would equal £1,184.20. And then you'd be done. It asks you for the nearest pound, so Y would equal 1,184 to the nearest pound. C. Use logarithms to find the number of years it takes to double your initial investment. So what we're dealing with now, we're dealing with Y is equal to your initial investment, which I might call I for initial investment, multiplied by 1.04 to the power of X. It asks you to find X so that your current amount of money is double your initial. So you're going to let Y be equal to 2 times the initial investment. So 2I would equal I multiplied by 1.04 to the power of X. Divide both sides by I, you would have 2 is equal to 1.04 to the power of X. Take logs of both sides, or natural logs. Ln 2 is equal to X ln 1.04, and that's bringing down the power of the X as well in one move. So X, putting X this side, would be ln 2 divided by ln 1.04. Ln 2 divided by ln 1.04. And that should tell us how many years. So we type in our calculator ln 2 divided by ln 1.04, and we get ourselves 17.6 years. So X is 17.7 years, or you might say X is 18 years to the nearest year. And we're done. We have our 7 marks. Next question, pause, have a go, then mark against mine. Right, let's break this question down into its parts. We're told a species of orchid is being studied. The population P the population P after a time of T years after the study is assumed to be this. This gives us a formula for the population after T years. A is some constant. Given that there were 300 orchids when the study started, show that A is 0.1. Well, the study surely started when time was 0. And therefore, you know, and also you know that the population at that time was 300. So you can sub in T is 0 and P is 300 into this formula here and work out what A is. So 300 must be 2,800 A e to the 0.2 times 0, which is just 1, over 1 plus A. Because again, e to the 0.2 times 0 is 1. Multiply by both sides by 1 plus A, you would get 300 plus 300A is equal to 2,800A. Subtracting 300A off both sides, 300 is equal to 2,500A. And dividing both sides by 2,500, 3,000 divided by 2,500 would equal A. Tap that in your calculator and you get, as required, A is equal to 0.12. And we've got those easy 3 marks. Next part. Use the equation with A is equal to this to predict the number of years before the population reaches this. So we are trying to solve an equation where we're told that P is 1,850. We are told that A is equal to 0.12. And we want to know T, what T makes that happen. Here is our equation, so let's use our equation. So I'm just going to write down one last time, 2,800. Actually, what I'll do is, let me just copy this over to the next page. There's our formula here. Let's just write our formula down with A is equal to 0.12. P is 2,800 times 0.12, 2,800 times 0.12, which is 336. Just makes our life a little easier when we're using the calculations later. 336 e to the 0.2t over 1 plus 0.12 e to the 0.2t. We're trying to find t so that it makes P 1,850. So let's do that. 1,850 is equal to 336 e to the 0.2t, all divided by 1 plus 0.12 e to the 0.2t. Multiply both sides by 1 plus 0.12 e to the 0.2t. On this side, if you did that to both, you get 1,850 plus 1,850 times 0.12, you get plus 222 e to the 0.2t is equal to 336 e to the 0.2t. Subtract 222 e to the 0.2t's off both sides, we would get 1,850 is 336 minus 222 is 114 e to the 0.2t. Dividing both sides by 114, you would get e to the 0.2t is equal to 1850 divided by 114, and that gives you, I'm just going to leave that as a fraction so we keep it accurate for now. And take luns of both sides and bring the 0.2 t down. So 0.2 t, this is taking luns of both sides and bringing the power down, is ln 1850 over 114. And to get t, you divide by 0.2, so it's ln 1850 over 114, all of that divided by 0.2. Tap that in your calculator, see what you get. And you get 13.93 years, which rounded is about 14 years. And you're done. Okay, next, part C. Show that P is equal to this. We want to show that P is equal to this here. we had already done that in the part above. We had already done that in the part above here by substituting in. So I'm not really sure where this question came from, but you know, putting in as before, A was equal to 0.12, you get for free that P is equal to 2,800 times 0.12 e to the 0.2t, all divided by 1 plus 0.12 e to the 0.2t, which simplifies to 336 e to the 0.2t over... Oh, it's not quite the same here. I realise that's not actually quite the same, because what they've done here is that they have factorised out on the bottom e to the 0.2t. They have taken that out as a factor. Now 1 divided by e to the 0.2t is e to the minus 0.2t, 1 over e to the 0.2t, and then you would have plus 0.12. Then the e to the 0.2t's cancel from top and bottom, and you get the simplified equation that they're looking for, 336 over 0.12 plus e to the negative 0.2t. So P is equal to that. So it was actually slightly different. And and I just realised there was another part that wasn't in my original question here. So going back here, I've slotted in, there was a part D that I missed out. So part D asks us, hence, using part C, show the population cannot exceed this. Well, the easiest way to do that is to let T go off towards infinity. Let T become an absolutely massive number. What would happen to P? Well, e to the minus a massive number would tend to 0. So P would start tending towards 336 over 0.12. And 336 divided by 0.12 would be equal to 2,800. The key thing here is that e to the minus 0.2t never equals 0, never equals 0. It asymptotes towards 0. So therefore P can't exceed this. It can't exceed 2,800. It never actually, in fact, would reach that, but it can't exceed it. And we're done. Okay, next question. Okay, let's go through this. A heated metal ball is dropped into liquid. As the ball cools, the temperature T, so it's temperature T, after little t minutes, after it enters the liquid, is given by this formula. So this formula tells us what the temperature is after a certain amount of time after the ball's been dropped into the liquid. Find the temperature of the liquid as it enters the ball. Well, that is when T is equal to 0. So capital T would be 400 e to the 0 plus 25. Capital T would therefore be 425 degrees Celsius. Simple. Part B. Find the value of T, the time for which T is 300. So we're using this equation over here that we had on the previous slide. This is the equation for the temperature, and we're letting T be 300. So we're saying 300 is equal to 400 e to the negative 0.05 T plus 25. We want to find little t here. This is our aim, find that, to make this equation work. Subtract 25 off both sides, 275 would equal 400 e to the negative 0.05 T. Divide both sides by 400, so 275 divided by 400 is 11 over 16, so 11 over 16 is equal to e to the negative 0.05 T. Taking luns of both sides and bringing the negative 0.05 T down, we would have ln 11 over 16 is equal to negative 0.05 T, and therefore T is this ln 11 over 16, that answer divided by negative 0.05, and that would give us what T is. Type that in your calculator. .49. You get 7.49 to 3 significant figures, and that's correct. 7.49 to 3 SF. Okay, next part. Find the rate at which the temperature of the ball is decreasing at the instant when T is equal to 50. Give your answer in degrees Celsius per minute to 3 significant figures. Now, we had a formula for temperature, and our formula for temperature was as follows, which I'm going to paste on this slide. The rate at which the temperature is decreasing is clearly dt by d little t. That is the rate of cooling. So we need to differentiate this with respect to T. So you'd have your 400. The differential of negative 0.05 T is negative 0.05, and you keep your E to the negative 0.05 T, and 25 differentiates to 0. This would therefore be equal to 400 times 0.05 negative that. You would have negative 20 e to the negative 0.05 t, and you were asked to find the value of that cooling when little t is 50, when time is 50. So dt by d little t when t is equal to 50 must be equal to negative 20 e to the negative 0.05 times 50. Tap that in your calculator and you will have the answer. So just tapping that in your calculator, you should get negative 1.64 degrees Celsius per minute to 3 SF. And you're done. And part D finally, from the equation for temperature in terms of T given above, explain why the temperature can never fall below 20 degrees. So get back your temperature formula here. If you let the time go off towards infinity, you let time go absolutely massive, T tends towards infinity, then e to the negative 0.05 T tends towards 0. So therefore, the temperature tends towards tends towards 25 degrees, and therefore clearly it can't ever be 20 degrees then, because it's falling all the time, and the lowest it could possibly be is 25, not 20. Next question, pause, have a go. Okay, first part. A certain drug is put in the bloodstream after T hours. The amount of it in the blood is given by this. X is d e to the negative an eighth T, where X is the amount of blood in the bloodstream and D is the original dose given. A dose of 10 milligrams of the drug was given. Find the amount of the drug in the bloodstream after 5 hours. You know that D is equal to 10 milligrams. You also know that T is in 5 hours. So if you want to work out X, you just substitute in. X is 10 e to the negative an eighth times 5. Tap that in your calculator, and with a bit of luck you should get 5.3, so you should get the following. X is equal to 5.353 milligrams given to 3 decimal places as the question asked. Okay, so here, this is slightly complicated, but I'm just going to draw a timeline to make sure it makes sense. Okay, what happened is, originally when time was 0, 10 milligrams was put in. And over the next 5 hours, so 5 hours later, when T was equal to 5, we worked out on the previous example that we still had 5.353 milligrams. Now this question is saying at that point then, another 10 milligrams is added. Okay, so in total, you would have in your bloodstream 15.353 milligrams at this point. And it's asking you how much will it have when t is equal to 6. Now, this is extra has been added in here, but the easiest way to do this is now think of this as t being 0. This is a new event happening. Think of this as t is 0, and think of it as saying what happens when t is 1. Using the formula, you know that the formula for this is x, the amount in the bloodstream, is the amount that was in at the start, e to the minus an eighth t. Now d is going to be this 15.353. That's how much was in at the start. So let's try this. X would be 15.353 e to the minus an eighth times 1. Tap that in your calculator. And you would get 13.549. 13.549 milligrams to 3 decimal places. The key with this question was a little picture to describe what was happening, and it makes it a lot easier. Part C, no more drug doses are given. At the time t after the second dose is given, the amount of the drug is 3 milligrams. Find the value of t at the time t hours after the second dose. T is now measured from after the second dose. Find the value of t. Well, we know our equation for this is x is equal to d e to the minus an eighth t. We are told that at t hours after the second dose, the amount of the drugs in the bloodstream is 3 milligrams. So we know x is 3 milligrams. We know the initial dose put in was like before, was 15.353. 15.353, and we're asked to work out t, this number that makes it happen. So we can substitute in 3 is equal to 15.353 e to the minus an eighth capital T. T is this magical time where the amount of drug in the bloodstream is 3 milligrams. Divide both sides by 15.353. So 3 over 15.353 is equal to e to the negative an eighth t. Take lns of both sides and bring down this power. So you would have ln of 3 over 15.353 is equal to minus an eighth times t. So therefore t would be this times negative 8. Okay, so it would be minus 8 ln 3 over 15.353. I think it's best if you keep everything in accurate form and then just round at the end. So t is negative 8 multiplied by the logarithm of 3 over 15.353, and you get yourself t is equal to 13.062 hours, or 13 hours to the nearest hour. And you're done. Okay, next part, it tells us it takes this many years for half the substance to decay. Find the value of C to 3 significant figures. Now we know that we have this formula R, and it tells us the number of atoms, and it's given by the formula 1000 e to the negative CT. Okay, now we knew from the previous part that when t was 0, R was equal to 1000. And it tells us how many years it takes for the substance to go to half. So we know that when t is 5730, R is half its initial value, which must be 500. We can substitute this information into our formula, and that will help us to work out what C is. So we know that 500 must be equal to 1000 e to the 5730, negative 5730 times C. That's substituting t is 5730. Divide both sides by 1000, minus 0.5 is equal to e to the 5730 times c. Taking luns of both sides and bringing down the power, ln of 0.5 would be negative 5730c. And I'm just going to make c this side. C must be ln 0.5 divided by negative 5730. So ln of 0.5 divided by negative 5730. Tap that in your calculator and you get 0.000121 to 3 significant figures. And you're done. Part C, calculate the number of atoms that we left at this time here. Now remember, we now know that C is 0.000121. We are also told time is 22,920, and we are asked to find R. So R is equal to 1000 e to the minus ct, so minus 0.000121 multiplied by 22,920. Tap that in your calculator and let's see what we get. So 1000 e to the power of negative 0.000121 22,920, and you would get yourself 62.45 atoms, which is approximately 62 atoms, which is hardly anything at all. And it's quite interesting to think it takes that long for us to almost reduce our atoms to zero. Okay, part D, on the space provided, draw the graph of R against T. Well, there's no space provided, but R against T. So R obviously goes along this axis, how many atoms, and T is time. We know that it started at 1,000 atoms. Is there any other information we actually worked out? We knew that it halved after 5730 years, and we knew one certain value, but it doesn't really ask you to plot those values here. We know it goes down like this, and it's asymptoting off towards 0 as time goes to infinity. It never gets there though. And that's it, we're done. Okay, next question, pause, have a go. Okay, this question is telling us that we've got some rabbits on an island, and the population P after T years is given by this equation. It asks to work out how many rabbits were first put on the island. That's when T is 0, so P would be 80 e to the 0, and P would be 80. So 80 rabbits were first put on this island. Part B, find the number of years it would take for the rabbit population to go past 1,000. So we want to work out when P is equal to 1,000. And we know that P is given by the formula. P is 80 e to the 5th t. Okay, so we're substituting in 1,000 for P, so 1,000 equals 80 e to the 5th t. Divide both sides by 80, you get 12.5 is e to the 5th t. Take natural logs of both sides and bring down the 5th t, so you would get ln 12.5 is equal to a 5th t. So t therefore must be 5 ln 12.5, and t would therefore be equal to 12.6 years. So 12.6 years. Part C, find dp by dt. Well, P is 80 e to the 5th t. So differentiating this with respect to t, it would be 80. The differential of a 5th t is a 5th. And then you would keep your e to the 5th t. So it would be equal to 80 times a 5th, which is 16 e to the 5th t. And we've done, there's dp by dt. And part D, find P when dp by t is equal to 50. So you're solving 16e to the 5th t is equal to 50. Divide both sides by 16. So 50 divided by 16 would be 3.125. Take logs of both sides and bring the 5th t down. A 5th t would therefore be ln of 3.125, and therefore t would be equal to 5 ln 3.125, and that would be t would be 5.70 years. Okay, that's what t is, but it asks us what the population is at that point. So you should keep working down the page. I'm splitting the page here just to make things a bit easier for me to write it. But you know the time it takes for this to happen, but it asks you for the population, and the population is given by the formula 80 e to the 5th t. So all you've got to do is substitute t is 5.7 in there. So p is 80 e to the 5th multiplied by 5.70. And if you do that, you would get yourself 250. So you would get yourself that your population is exactly 250 rabbits. And now we're done. They are all the past paper questions on exponential growth and decay that have arisen on the Edexcel Core 3 syllabus. I hope you found the following useful in your revision.